This is section 2.3. We're going to be talking about Venn diagrams and set operations. I know I mentioned a Venn diagram when I was covering the last section. I expect that you've probably seen most of them before, and even if you haven't, you should make sense of it after watching this video. Okay, so definitions, conventions, notation, that kind of stuff. The universal set, which is always symbolized by the letter U, is the set that contains all of the elements under consideration in a given discussion or problem. So if we're talking about all the people in the world, that could be the universal set. A Venn diagram is a way of representing sets using circles, usually within a rectangle. All elements of a set would be inside the circle representing the set, and the rectangle represents U. So if I had two sets here, everything that belonged in set A would have to be inside set A circle. Everything that belonged in B would be in here. And then everything under consideration would be somewhere in this rectangle, possibly not in one of the circles. Most of the time, we're going to end up dealing with Venn diagrams that look more like this one, but we're going to get there. Okay, so disjoint sets. These are sets that have no elements in common. If they have absolutely nothing in common, you're going to have a Venn diagram that looks like this. There's no overlapping of the circles. There's nothing that I could put inside this circle, and it would also be inside this circle. Okay? Proper subsets, and this is what I mentioned in the last section, can be represented like this. B is totally inside A, so that everything I could possibly put inside B is also inside A, so it is a subset. And also they're not equal. So because they are not equal, then it is a proper subset. Equal sets can be represented with a Venn diagram like this one. They are exactly the same, so the circle is exactly the same. You could have a regular subset that looks like this. Never a proper subset. Okay, sorry about that shake right there. So let's look at this. Like I said, more often you're going to have something in common, or at least the possibility of something in common. You're usually going to see a Venn diagram like this, and later we're going to work with some that are 3 circles, not just 2. Okay, and so now we're just going to start using these things to try to understand what's going on. All right, the complement of a set. The complement of set A, which is written like this, A prime. That's what the little line up there is called, A prime, is the set of all elements in the universal set that are not in A. In set builder notation, this is represented like this. The complement of set A is everything that is in set U, but is not in A. So if I were just going to show that on this Venn diagram, the complement of A would be everything in here, everything here, everything like that. As long as it's not inside A, that's its complement. So it's exactly the opposite of it. Okay, so let's look at a couple problems. Here we are given the definitions of some sets for these problems, and they're going to ask us to find these things using the roster method. So basically, list everything. To find A prime, or the complement of A, here's my A set, here is U. I'm just going to write down everything that is not in here but is in here. So A is here, B, C is not over here, so this is going to be C. There is no D in here, no E, but there is an F and a G. So basically, when you're comparing these two, what's missing from A? Well, C, D, and E. Okay. For here, B prime, or B complement, sorry, I have C, D, and E, and I want to write down everything that is in U that is not here. So that would be A, B, C, D, E, F, and G. Roster method requires the braces, so that would be your answer. The complement of C would be, well, there's A, B, C, D, E, and F, and then G. And the complement of D, well, these are almost the same size. So what is the difference? This one has a G and this one does not. So the complement of D would be the set that contains G. Okay. Now, some definitions. Okay, we have certain what we call operations that we are going to do on sets. You know, operations are ways of combining things or working with things. In arithmetic, we have addition, subtraction, multiplication, and division. We have sort of similar things happening here. Just how do we work with these things? When we're talking about the intersection of sets, intersection, which is written like this, with a little hump, rounded hump, this is the set of elements that are common to both set A and set B. In set builder notation, the intersection looks like this. The set of all x such that x is an element of A and x is an element of B. This word right here, and, is very important. Not just in this section or this chapter, but it also be very important in chapter 3 as well. Okay, so when you have and, we're looking for the stuff that they have in common. And if you're talking about a Venn diagram and we wanted to represent the intersection of A and B, this center part right here, the overlap, would be shaded. So visually, this is the area of the intersection. Now, union, okay? As English speakers, this is where we get messed up a little bit. Okay, the union of sets A and B, which is written like this, so it's basically the same symbol as intersection, just flipped over, is the set of elements that are members of set A, set B, or both sets. In set builder notation, the union is written like this, the set of all x such that x is in A or x is in B. That keyword is very important. Now, one of the things we have to be aware of is that there are two different versions of the word or. There's inclusive or and exclusive or. In exclusive or, which is pretty much what we have in English, we hear it best, well, I hear it best in my mother's voice, but if your dad was the disciplinarian, your grandmother, whoever it was, imagine this in their voice. You can have cake or you can have ice cream. What's going to happen if you go get both? Well, my mother anyway, if she said it like that, I was going to get trouble if I got both. So that's the exclusive or, A or B, but not both. In math, with sets, with logic, we use inclusive or. So whenever we, as English speakers, read union, we need to hear A or B or both. If you look at it in a Venn diagram, it would be everything that's in A, everything that's in B, and everything that's in both. So that just sort of picks up everything inside here. This one's interested only in the overlap. Okay. Now, dealing with the intersection and union with the null set, or empty set, sorry. This is saying A intersected with the empty set. This is saying what do they have in common? It doesn't matter what A is. What do they have in common? Well, there's no elements in here for there to be in common with A. So what do they have in common? Nothing. So A intersected with the empty set is the empty set. Okay? Now let's change it to union. A union the empty set. What this does is it picks up everything that's in A, everything that's in the empty set, and everything that is in both. Well, everything in A is A. Everything in the empty set, well, there's nothing. And the stuff they have in common, well, that's also nothing. So you get the same thing here. What you should remember from this, you can think about it a little bit and you'll get it right, but the main thing you should remember is that whenever you're using the empty set with intersection or union, you're going to have one of these two possibilities. It's either going to disappear completely or you're going to end up with the same thing you had. Okay? So, some bigger example problems. Here are my sets that are given to me. 1, 2, 3, 4, 5, 6, 7, 1, 3, 5, 7, 1, 2, 3, 2, 3, 4, 5, 6. We're supposed to use the roster method to write down each set. So here I have B union C, I have B intersected with C. So union, that is the word or. So what I'm going to do is I'm going to list on everything that is in B, or is in C, or is in both. These numbers do not need to be in numerical order, although it does make it a lot easier to check if you do that. So I'm going to try to do that. I have 1, I have 2 and 3. Okay, so there's the 2 and the 3. Now this one also has 4, 5, and 6. So the union of these two sets would be this. Yes, you have the 2 listed twice, the 3 listed twice. That doesn't matter. You don't have to, you can list things twice theoretically, but it doesn't do you any good. And I think the computer might count it wrong. All right, let's look at B intersected with C. And that's just asking, well, what do they have in common? This has a 1, but it's not here. They have a 2 in common, a 3 in common, and that's it. So the intersection would be just 2, 3. Okay? So let's look at a complement. So what this is saying is we want everything that is not in A, but is in here. Well, these are just the odd numbers. So 1 is there, but 2 is not. And then 4. There's 5, and then 6. Okay. Now this one sort of involves a bunch of other things. So this is a multi-step problem here. I have the complement of B intersected with C. The first thing I need to do is I need to understand what pieces I have here because I'm not given the complement of B. So I need to figure out what that is. So B complement is everything that is not in here but is in here. So I have 1, 2, 3, knock that out. B complement would be 4, 5, 6, 7. Okay, now I want to do B prime, the complement of B, intersected with C. So what do these have in common? Not a 2, not a 3, but they do have a 4 in common. Okay, they do have a 5 and a 6. So I needed this little piece first, and then I compared this to the C I was given to get here. Okay, now let's look at A intersected with B, inside parentheses, complement. Parentheses in these sets work the same way as they do in arithmetic. It means you need to do that part first. So the first thing I need to do is I need to figure out A intersected with B, which is simply what do A and B have in common? 1 and 3. Okay, so now if I want this, the complement of this, it just cannot have 1 or 3 in it. So I go to U and I start listing the things that are not 1 and 3. So 2, 4, 5, 6, 7. Okay. C union the empty set. Now I see the empty set, so I know this is one of the special cases. This is union, so that means or. That would mean I need everything that is in C, or in the empty set, or that's in both. This is going to be simply C. It takes everything that's in C and you would add to it anything that's in this set or is in both, and there's nothing in here or in both, so the answer is just C. Likewise here we have the empty set again, but it is intersection. So what do the set B and the empty set have in common? Well, there's nothing in here to be in common with B, so this is the empty set. Okay, so now let's do these last little bits here. And I realize I cannot get all of this on the screen at the same time as here. Okay, so I'm going to build this up in pieces as well. Well, no, I guess I don't need to. We've figured out A intersected B. We have that information right here. We figured out B prime. We did it right here. So my pieces, just pulling from the problems we've already done, A intersected with B is 1 and 3. The complement of B was 4, 5, 6, and 7. Okay, so now that I have these two pieces, this is this set right here and here, and what I'm supposed to be doing with these two? Union. So I want everything that is in here, or that is in here, or that is in both. So I start listing the things that are in either of these two sets. Well, that's 1, not 2, 3, 4, 5, 6, and 7. All right. Here. A union B intersected with the complement of B. Well, A union B, we're going to have to come back up here. I want to pick up everything that's in either one of these or in both. Well, 1, 2, 3, and then 5 and 7. 1, 2, 3, 5, 7. So I have A union B here, and I also have B prime written right here. So I'm asked to intersect them. So what do these two have in common? Well, there's no 4 here, 5, and no 6 and 7. So this is just 5 and 7. And that would be your answer there. Okay. One last page of notes. All right. The formula for the cardinal number of the union of two finite sets. We're not going to deal with infinite sets here. We don't want to do that at all. And remember that the cardinal number of a set is how many elements there are in a set. Okay? So if you want to find the number in the union, you take the number that are in A plus the number that are in B, and then you subtract away the intersection. Now, why would that be? Let's just look at this Venn diagram that happens to be here. If I were wanting to count the number of elements inside A union B, would be everything inside these two circles. If I wanted to count the number that are in A by itself, I would have 4. So let me just write that here, 4. The number of elements in B, I have 5 elements in there. Now, if I just add those together, I get 9, but you can see here, 2, 3, 4, 5, 6, 7. You can count on this one and see that there are 7 elements in the union. Well, why is that? It's because we counted the 3 and the 7 twice. It's part of A, which is up here. It was also part of B, so it's included in here. So since this region was counted twice, we're going to subtract it off once. So the number that are in the intersection is 2. So this would be 9 minus 2 which is 7 elements, which is exactly what we can see from here. Okay, so let's do this as a bigger problem. Set A contains 12 numbers and 18 letters. Set B contains 14 numbers and 10 letters. One number and 6 letters are common to both. Find the number of elements in set A or in set B. Okay, well, this isn't bad at all, but the tricky part is that we do have to take into account that we have two different things. They give us these two different numbers, wanting to mess us up a little bit. Set A, the number of elements in set A, we have 12 numbers and 18 letters. Therefore, the cardinal number of set A by itself would be 30. Don't just go with these numbers right here. Don't just look at them. You have to realize that you should be adding them together to find out the total number. All right, the number of elements in B is 14 numbers and 10 letters. So 14 plus 10, that's 26, or 20, I can't add, 24 elements. Okay, and then the numbers that are in common to both, that would be the number in common to both would be A intersected with B, is 1 number and 6 letters. Okay, so now if I want to figure out the number of elements in or A or B, that means union. So the number in A union B, see the formula up here. This is the number inside A, which is 30, plus the number that are inside B, which is 24. And then you subtract off the number that are in the intersection, which is 7. So when you do this arithmetic, you get 54 minus 7. So the cardinality would be 47. Okay? So for this last problem, we're going to use this Venn diagram and answer these questions. Make sure that you note the difference between when you're just being asked to do something to a set and when you're asked to find the cardinality of that set. Okay? So, A intersected with B. We're not asked the cardinality. We are simply asked to find out what the intersection is. If you do not have an N in front, your answer will be a set, which means it's either the empty set or you need to be listing things between braces. If you have an N in front, you're just going to get a simple number. A intersected with B. We're not asked for the cardinality. That means we want to find the things that are common to A and B. And that would be right here in the center where our two circles overlap. So the set A intersected with B would be 3, 7. Okay. Now the number in A union B, well, I use this as an example up above, but just looking at this, what I would recognize is, okay, the union of A and B would be everything that's inside the circles in total, and then I would just count them up. 4 plus 3, that number is simply 7. And it's not a set because we're asked for the cardinality of it. Okay. The number of elements that are in the complement of A. So what this is asking is we want to know how many numbers are not inside the circle A. So I'm going to cover up those 4. And I have 1, 2, 3, 4, 5 elements. You can't lose the stuff that are in the universe, but not in one of our sets that we're specifically talking about. So these things are in the world, 8 and 9 are in the world we're talking about, but not the particular sets inside that world. Okay, so let's find A intersected with B and the complement. So basically what this is saying is give me everything that is not in the intersection of A and B. Well, the intersection is right here, 3, 7. We figured that out right here. So the complement of it will be everything inside the rectangle that is not 3 or 7. So this is 1, 4, 2, 5, 6, 8, 9, and I just went in order right through there, and so they're not listed in numerical order. You can rearrange that. It technically doesn't matter. Okay, let's find the complement of A union B. So we want everything that is not A along with everything that is in B. Well, let's just build this up. What would A prime be? It's everything that's not in A, so 3, 7, 2, 5, 6, 8, 9. No, not 3 and 7. Those are in A. I'm sorry about that. It's going to be 2, 5, 6, and 8 and 9. Okay. Now I want to union that with B, so I'm going to take this and add to it everything that is also inside B. And this is where I got the 3 and the 7, because the 3 and the 7 are inside B. So if I take this set and union it with B, I get 2, 5, 6, 8, 9, and then the 3 and the 7. Okay, now the last example problem. We want to find the cardinality of U minus the cardinality of B. So how many elements are there in the universe? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be 9 minus, how many elements do we have in B? 5. So 9 minus 5, this answer would be 4.